In this video we're going to be taking a look at a new perspective on operation order. So we're going to be observing what I consider a sort of illusion of ambiguity when it comes to operations, and we're going to introduce a new concept which I call bound pairs in order to resolve this ambiguity. So let's just quickly talk about the order of operations. So the order of operations is a critical rule in mathematics which serves to standardize the interpretation of arithmetic expressions. It's commonly understood through various acronyms, so for example PEMDAS is one of them. So the P means parentheses, E means exponents, MD means multiplication and division, and AS means addition or subtraction. And there are slight variations to this amongst authors. So the purpose of rules like this is to resolve ambiguities. So for example, if we have an expression 3 plus 5 multiplied by 2, we want to figure out should that evaluate to 13 or should that evaluate to 16, for example. However, we notice that the order of operations is not really a fixed property of mathematics, but rather a notational convention. It allows for the consistent disambiguation of expressions, whether that be in mathematical works, in teaching environments, etc. So in this video, we're going to be arguing that the conventional order of operations is often misunderstood, and that some of the ambiguity it intends to resolve is only that of an illusion. By investigating a novel perspective where operations are treated as what I call bound pairs, we can eliminate same operation ambiguity entirely. So this approach is going to align well with the associative property of arithmetic operations, and as a result it will provide an indisputable basis for when parentheses are required. So we're going to kind of delve into this intuitively to begin with, and then we'll go ahead and formalize everything rigorously at the end of the video. And I'll also let you know that this entire video is available in article form as well, so there'll be a link to that in the description below. And if there are any errors or omissions in this video, then the kind of corrected up-to-date version can be found in that article. So we'll begin by discussing the ambiguity we face with operations. So let's consider a simple example. So we're going to have an expression 10 divided by 5 multiplied by 2. Now, according to the conventional rules, we evaluate multiplication and division from left to right. So that results in 10 divided by 5 in parentheses multiplied by 2, which equals 4. However, another interpretation could be to first perform the multiplication, resulting in 10 divided by and then 5 multiplied by 2 in parentheses, and that's then equal to 1. So this discrepancy has resulted in heated debates in mathematical communities, especially when additional concepts such as implied multiplication are factored in, since implied multiplication usually takes increased precedence. So this issue arises from an often too prevalent choice to treat multiplication and division as distinct operations, individually having their own slot, so to say, in the evaluation order. This perspective separates the division of 5 from the multiplication of 2, even though multiplication and division are conceptually linked as inverse operations. However, even when one unifies these operations where multiplication and division are evaluated simultaneously, many still insist that we must have a left-to-right evaluation rule in place to minimize ambiguity. However, it's completely reasonable to dislike the choice of left-to-right evaluation, considering it an arbitrary choice that's prone to human error. As a result, it is common to include redundant parentheses for the sake of apparent clarity, citing the circumvention of error as a rationale. We propose that this apparent clarity originates from a fundamental misunderstanding of associative operations. Instead, we shouldn't feel anxious when parentheses are omitted in certain expressions, but rather embrace it. We'll be reinforcing this claim through the introduction of what I call bound pairs. So before we can introduce the notion of bound pairs, it will be vital for us to recap our understanding of what it means for an operation to be associative. So recall that an operation is associative if and only if the grouping of operands using parentheses does not affect the final result. In precise terms, we define an operation plus to be associative if a plus b in brackets and then plus c is equal to a plus and then b plus c in brackets, for all numbers a, b and c in the domain of the operation. For example, addition and multiplication over the real numbers are indeed associative. It does not matter what pair of operands we evaluate first. However, subtraction and division, on the other hand, are not associative. So you can quickly find a counterexample where associativity is not upheld. So this non-associativity is precisely why, in the goal of avoiding ambiguity, we demand parentheses. But this ambiguity only exists insofar as we handle operations like division and multiplication as binary operations. If instead we consider division as a unary operation, bound to the number it operates on, e.g. divided by 5, we realize that our typical understanding of when parentheses are required is misapprehended. It's now time to express this notion in detail. So we're going to construct a new definition of operation order based on bound pairs. So let's go ahead and look at that. So recall that the conventional interpretation of operation order involves processing the expression in binary chunks from left to right. This interpretation leads to the idea that order matters because rearranging the sequence changes the result. Therefore, comfort is frequently sought in the inclusion of redundant parentheses. Surprisingly, however, this is not the only strategy for determining the necessity of parentheses. The apparent ambiguity arises not because the operations themselves require specific order, but because we separate the operations from the number they act on. Let's see exactly what we mean by this. So consider an arbitrary multiplicative expression. In our expression, let's bind each operator with the substance that follows it, forming a pair. We call this a bound pair. Let's explore this idea with an example. In the expression 10 divided by 5 multiplied by 2, we find one of the pairs to be divided by 5, since 5 follows the division, and we have another pair multiplied by 2, since 2 follows the multiplication. Additionally, notice that there is an implicit multiplication by 1 at the beginning of every multiplicative expression. So in the expression 10 divided by 5 multiplied by 2, we can equivalently write 1 multiplied by 10 divided by 5 multiplied by 2, which actually forms 3 operator-operand pairs in total. So number 1 is multiplied by 10, number 2 is divided by 5, and number 3 is multiplied by 2. Now, when we talk about rearranging an expression, we shall only rearrange entire pairs at a time. In particular, we treat these pairs as inseparable units. Carefully observe that we are no longer permitted to rearrange binary chunks, such as 5 multiplied by 2. Instead, we are only swapping tightly coupled pairs, such as the multiplied by 10 portion or the divided by 5 portion. So an example rearrangement is as follows. So the first pair is multiplied by 2, the second pair is multiplied by 10, and the third pair is divided by 5. So this then simplifies to 2 multiplied by 10 divided by 5. So what's key to notice here is that this rearrangement is equivalent, as it evaluates to the same value. This perspective changes the way we interpret an expression. Instead of seeing it as a tree of binary operations, we see it as a sequence of operator-operand pairs. It is in this new definition of operation order, where we consider this alternative notion of rearrangement, that we notice the insignificance of operation order. There is no significance in evaluating left to right, for any rearrangement we choose results in the same outcome. By strictly maintaining these pairs, we can rearrange the expression without altering the result, but it is essential that the integrity of the pairs is preserved. When we work with this notion of operation order, it is clear that parentheses serve no purpose in achieving clarity. When it comes to operations of the same family, such as multiplication and division, they belong together as they are just inverses. In summary, this method relies on viewing each operator as inherently linked to their right-hand operands, such as divided by 5 having the division coupled with the 5, and multiplied by 10 having the multiplication coupled with the 10. By respecting these pairings, we effectively eliminate the illusion of ambiguity that motivates our use of parentheses. And I do want to emphasize that this is only when we're talking about kind of operations that are part of the same family. So if we have addition and multiplication, we might still need to use parentheses, and we will be talking about that more later. So now we're going to move on to the justification of the proposed definition. So note that we can't simply redefine operation order without seeking appropriate justification. We will justify this definition through 2 observations. First, notice that the notion of bound pairs is nothing new. It is already the predominant choice when rearranging additive expressions, consisting of sub-expressions bound to one of the unary operations, plus or minus. In the case of 1 minus 3 plus 4, we treat plus 1 minus 3 and plus 4 as units, allowing us to rearrange them to our pleasing. We are so familiar with this act already that it typically goes unnoticed. Pay attention to how parentheses are rarely included in additive expressions, and how the implicit identity element 0 is omitted from the beginning of additive expressions as well. Secondly, notice that our new definition is fully compatible with the expectations of operation order that we would expect, namely that it is a satisfactory decider on whether parentheses are required in expressions. It means we don't have to rely on a prescriptive rule insisting on an arbitrary left-to-right evaluation order. Notably, there are no obvious downsides to this approach. Instead, it greatly eliminates confusion when it comes to families of similar operations. It is clear that we only require parentheses if we disrupt the natural pairings in our writing, something that should be taught to be avoided. In summary, this new definition of operation order is more consistent because it aligns directly with the need for parentheses and is comparable to our existing approach in additive expressions. The conventional interpretation, while technically correct, does not do justice at highlighting the fundamental nature of associative operations. Next, we're going to look at so-called families of boundary associative operations. So with this newfound system in place, we can define an operation, such as division, to be boundary associative if there exists another operation, one that's associative, in this case multiplication, where a division can instead be described as a unary operation when combined with multiplication. And this is precisely what's going on when we're interpreting these expressions as bound pairs. So if we have 2 divided by 7, we can instead interpret that as 2 multiplied by the inverse of 7. So the division is kind of connected up with that 7 in such a way that it can be reinterpreted as a unary operation, which is the inverse. So from that, we can then study the entire family of boundary associative operations originating from a particular associative operation, such as multiplication. So for example, division is part of the same family as multiplication, because it can be rewritten as the multiplication of this unary operation, which is the inverse. So some operation is boundary associative if there is some other operation that's associative, and we can kind of transform that boundary associative operation into the other one by forming this unary operation. So now that we've kind of tried to get some intuitive explanations of everything in this video so far, we're now going to move on to formalizing everything rigorously. So let's describe our new approach in mathematical notation. And if you're not fully familiar with the style of mathematical writing, this might be a little bit difficult to comprehend, but hopefully you can have a go at following along. So we're going to begin with definition number 1. So let A, B and C be sets where A and B are subsets of C. And we're just going to need these sets in order to specify the domain and the range of various functions, so don't worry too much about that. So then we're going to call an operation slash boundary associative under particular criteria. So note that this binary operation slash takes in 2 elements, so that could be 2 numbers for example, but in order to make this a general definition, it doesn't necessarily have to be numbers, it can be any operation, and it will take in an element from set A and another element from set B. And then it returns an element from set C. And the reason we have A and B being a subset of C is so that it's not taking in elements that it can't possibly return. So this operation slash, we're going to call that boundary associative if there exists a function slash dash and also an associative operation star that follows certain criteria. So slash dash is kind of the unary equivalent of the original binary operation slash. So instead of taking in 2 elements from sets A and B, it just takes in a single element from set B and still returns an element from set C. So remember earlier when we were discussing bound pairs, and we were saying we were interested in what was on the right of a particular operation. So this is why we're constructing this unary operation that is taking in that element from the right, so the one from set B. So then we're also looking for an associative operation star, and don't worry too much about the inputs and outputs of that. And the idea is that A divided by B is the same as A multiplied by slash dash of B, for all A in A and B in B. And this binary star operation is taking in an element from A, and then it's taking in an element from the image of slash dash. And what that just means is any possible element that slash dash can return, that's the image of slash dash. So that's just constraining our input a little bit, but don't worry too much about that, and then that returns C. So let's just go over that again. So we're going to call an operation slash boundary associative if we can find some unary function slash dash and also a binary associative operation star such that A slash B is the exact same as A star slash dash of B. So in this case we say that slash also boundary obeys star. It kind of means that slash has kind of a similar structure to star. It's kind of obeying or resembling its associativity, but in a different way. And that's where the idea of bound associativity comes in. So now we'll move on to definition number 2. So let star be some associative operation, and let B sub star be the set of all boundary associative operations slash that boundary obey star. So what we're doing is considering the set of all operations that kind of resemble each other. and in this case that resembles star. So we're going to go ahead and call that b sub star. So we then call b sub star the family of star, so that's the name we're going to give this special set. And we also set slash sub star to the identity in b sub star. So for every associative operation, if we have a unary operation that's just the identity function, so it doesn't change the input in any way, so this would just be the same as the original star operation. And so that's why we're giving it the name slash sub star. So furthermore, let slash sub 1 and slash sub 2 be some arbitrary elements from b sub star. So we're picking two of these unary operations from the family of star. And then we'll say that slash sub 1 and slash sub 2 are boundly equivalent. And the idea behind that is that the operations are certainly not equivalent, but they have this key similarity, this key resemblance between them as they're part of the same family, and so we call them boundly equivalent. And so we have a notation for this, so we write slash sub 1 is equivalent with a little b on top, and slash sub 2. And so that b on top of the equivalent symbol means it's boundly equivalent. Okay, so I hope that wasn't too complicated, so now let's move on to definition number 3. So let star be some associative operation, and let slash be an operation in the family of star. So like we described earlier on in this video, we will call slash and b together a bound pair of star, where b is in the domain of slash. So this definition just allows us to refer to these pairs. So with all these definitions in place, we can now move on to theorem number 4. And this theorem is going to reveal the fact that rearranging these bound pairs has no impact on the final result. So let star be an associative operation and I sub the natural numbers be an index set. So don't worry too much about this index set, it's not too important, it just allows us to iterate over all the possibilities. So then let's construct a finite sequence of bound pairs of star, and we just have this notation here where we're considering all pairs slash I, slash sub I and b sub I, where I just goes over this index set. So let that be a finite sequence of bound pairs of star, and then let's consider a rearrangement of this. So we have a new sequence, it's the exact same except it's only a rearrangement of the original sequence. So in this case we're going to use the j subscript when we're iterating over all the possibilities. So then the theorem says that applying this associative star operation for whatever number of times necessary, where in each case we take the unary slash operation of the right hand side, so that's b, and that's equal to the exact same thing but using j's instead of i's, so it's part of the rearrangement. So for all the j's we're applying the star operator, and we're making sure this element b at this index j is going through this unary slash operator at that index as well. So don't worry too much about the notation there, but that's the key idea of the theorem. Here this indexed star notation is just a repeated application of star. So it would be the same thing if you've ever seen the summation notation, which uses capital sigma, or the product notation, which uses capital pi. But in this case we're considering some arbitrary operation star, but we're using the exact same notation here. Okay, so with that out of the way, we're now going to move on to remark 5. So let star be once again an associative operation and I sub n an index set. Now in the last theorem I should clarify that I was actually a proper subset of n, which means it's not infinite, as anything can actually happen when you're rearranging infinite sequences, so that theorem doesn't apply, but you don't have to worry too much about that. But in this case we might be working with an infinite sequence, so I could indeed equal n. Anyway, we're once again going to consider this sequence of bound pairs. So we have pairs slash sub I and b sub I for all the I in the index set. So now we're going to describe the notation for how we write this down, and that's the purpose of this remark. So here the 0th index is going to mean the first element, and the 1th element is going to mean the second element, etc. So we'll start by writing the first slash operation, and then followed by the first number or whatever element that is that we are acting on. So that's slash sub 0 and b sub 0. And then we'll move on to the next one, so slash sub 1, b sub 1, and so this keeps going on depending on how many pairs we have in this sequence. So we define this new notation as being identical to this original notation, where we repeatedly apply star based on this index set, just like we had in theorem 4. So this is just giving us that familiar notation that we'd like when we were writing down these sequences of bound pairs. Furthermore, we may omit the first operator, slash sub 0, and just simply write b sub 0, slash sub 1, b sub 1, etc., provided slash sub 0 is equal to slash sub star. So what we're saying is if the first operator is the identity function, so it has no impact on the final result, then we can just go ahead and omit that entirely. So that resembles that familiar idea where if the first unary operator you have has no effect, you can just go ahead and omit that. So take some additive expression plus 5 minus 7. You don't need to write that plus at the start, you can just write 5 minus 7. So this is the same thing here. So if the first operator slash sub 0 is equal to slash sub star, which is the identity operator, then you can go ahead and omit that. So that's this remark out of the way, but I'd also like to clarify for the indexed star notation that we were using. If we are in the infinite case, it refers to the limit of the partial applications of that operation, if it exists. But don't worry too much about that, that's just if there's an infinite number of operations. We can't just nicely apply it infinite times, so instead we have to take the limit. So that's all our formalization out of the way, so it's now time to recap everything we've covered in this video. So first we discussed how the order of operations, commonly summarized as PEMDAS, is a notational convention and not an inherent mathematical property. It standardizes interpretation and avoids ambiguity. Then we have seen how ambiguities arise in expressions like 10 divided by 5 multiplied by 2, where the conventional left-to-right evaluation can conflict with alternative interpretations. This is due to treating multiplication and division as distinct operations rather than linked as inverses. Then we have observed how associativity applies to addition and multiplication, but not to subtraction and division, necessitating parentheses to avoid ambiguity. However, the need for parentheses is often exaggerated due to a misunderstanding of operation grouping. If we have operations from the same family, we do not need parentheses. So then, by viewing operations as bound pairs, each operator is inherently tied to its right-hand operand. This approach eliminates the need for left-to-right evaluation rules and reduces reliance on parentheses for clarity. So then we provided some justification. So the bound pairs method aligns with existing practices in additive expressions where plus and minus bind naturally and offers a consistent intuitive framework for interpreting mathematical expressions without arbitrary rules. And finally, we looked at formalization. So we showed how the formal definitions of bound associativity, bound obedience, families, and bound pairs precisely capture the essence of this approach and allow for the formal notation to be conceptualized for expressions involving bound pairs. So in conclusion, the standard order of operations has long functioned as a tool for disambiguating mathematical expressions, but it often introduces unnecessary complexity and misunderstanding. Some of the ambiguity it aims to resolve only exists because we separate operators from the right-hand operands they interact with. By reinterpreting expressions as sequences of bound pairs, we simplify the evaluation process, eliminate arbitrary rules like left-to-right precedence, and reduce dependence on parentheses. This approach provides a more intuitive and consistent framework for understanding arithmetic expressions, moving beyond the limitations of conventional notation. Embracing this perspective can simplify boundly associative expressions and clarify the true nature of mathematical operations. Thank you so much for watching this video, and if you've enjoyed, please don't forget to leave a like, and I'd love to hear your thoughts on this topic in the comment section below. Whether you agree or disagree with me, I'd love to hear your opinion. And don't forget to check out the article form of this video in the description below. It might be kind of easier to read through everything at your own pace, rather than me potentially rushing it in this video. Okay, so I hope you found this exploration interesting, and I will see you all next time.